Okay, moving on to Objective 4.3. This is kind of a middle step, or it falls. You can do this in your pre-processing. You can also do this kind of in between pre-processing and processing. So it is a type of geometric correction, because what it does is it kind of fills in the noise or reduces the noise that you're seeing in an image, or else it can enhance as well the image so that you can see more of what you need. So here we have filters, and the filtering side of things, there's two major categories that they fall into. One is spatial filtering and the other one is frequency filtering. So the first filtering we're going to look at is spatial filtering. And spatial filtering uses something called a convolution window or kernel. So this is like a square grid. So you can think of it as a kind of like if you were to take a bunch of wood and you created a grid and then you put like a coffee filter underneath it. It's kind of the same idea with this. It does need to have an odd number of rows and columns, so therefore it has a center pixel that we're looking at. And then all the math that we apply within that entire filter will be applied to the center of the pixel. Now, filters can be any size you like. What is key with these filters, though, is the bigger they are, the more impact that they have. The smaller they are, the less impact they have. So for the first one, we have smoothing linear filters. So this one just takes an average. It's known as averaging filters. It's also known as mean filters. So we take the average within the window. So that means, so if you see here, for example, I have my original image. And it's so 15, 9, 32, blah, blah, blah. These are all digital numbers. I'm going to place my mean filter over top, which would be a 3x3 filter, because I want to filter the middle number. So I put it on top, and I take all the numbers that I find in my image. So that would be, I'd add up all 3 rows, including the center pixel, and then I divide it by 9, then I get 18.7. That 18.7 is the new value of my image. Then when I go to do a different one, let's say I had a bigger image and I wanted to filter the 11 over here, then I would move everything over and I would have like 9, 32 and whatever the number is there, then 30, 11 and that number there, and 15, 13 and that number there. And then I would calculate what this new pixel is going to be. Note that I didn't get rid of the I didn't use 18.7, but I used 30 for the next one. Always go back to your original image. Do not compile all your results, right? Because if you continue to compile all your results and you keep going over here, then all of these numbers that you have filtered are actually filtering additionally on top of it. So it's like almost like an exponential filter, and we do not want that. You want to just apply the same filter every single time for each individual pixel. They need to be done in a independent manner. So you can think of them as, okay, this 30 is its own thing, so I apply the filter just to that one. And then I have to go back and think, okay, this 32 is its own thing, so I'm going to apply the filter just to that one. So you can see what a linear filter does, so it just kind of smooths it out. Why would we do that? Well, when you're dealing with satellite imagery, we're often dealing with natural features. And a lot of things are actually fuzzy boundaries. So for example, a forestry boundary, it kind of transitions from like trees to short trees to bushes to long grasses and such. Where does it actually end? So what we often do is smooth it over until until like a little bit more of a defined edge comes out. So that's one thing. We can also do smoothing filters over urban areas because there's so much going on. And for like, okay, we want to identify the edges of the city. What will happen is it'll identify like every house edge, right? So if I'm looking at every house edge, that really doesn't give me the edge of the city. So I have to, I would apply a smoothing linear filter so I can cover that. If we look at Calgary, for example, it might actually split the city in half if I didn't apply an averaging filter, because the river goes right through the middle of the city and it would identify the northwest or like the northern part of that as part of a city or its own city, and then the southern part of it as its own city. So if I can smooth it out and like get rid of that river in the center, then that allows me to identify those edges better. The other one is a weighted filter, or weighted average filter. So this time around we're applying weights. So you can see here this red is my convolution kernel. So this is my filter, and this is my original image. And so what I'm doing is I multiply each pixel with itself. It's almost like a dot product, so you can think about it in that way, sort of. If you remember that from from doing linear algebra. So we go like 0.25 times 15, and then 0.5 times 21, and etc. So this 21 up here is incorrect, so just that should be 15 instead. And then these numbers, just kind of ignore those. That's interesting. I will have to change that. So the idea though is that this 0.25 goes onto this 15. Now, if I had shifted down and I was actually going to be working on like the 0.5, then this makes sense, because then my 0.25, this here would go onto the 21. This part here goes to the 30 and it goes onto that one. This should be 0.2, or this is 0.5. Nope, this should be 0.25 times by the 11. So just ignore this math on here. I will make sure it's changed for the actual PowerPoint. But it would be applied to the 15. Then you would divide by the sum of the weights. So you would add up this entire box here. So that would be 0.25 plus 0.5 plus 0.25, etc. And that becomes 4. So that's why this number 4 is there. So we multiply each weight by the value, and then we add it all up, and then we divide that whole sum by 4. And that would give us our new answer. So you can see from the previous one, this is 19.6, and the other one was 18.7. So there is actually a difference. And the reason that we can't say one is right and one is wrong is because it depends on the application that you're dealing with. And weighted filters, sometimes you can control the impact of certain errors by using a different weight in the area. So that's where the weighted averaging filters will come in. It gives you more localized control. Then we get into order statistics filters. These are still falling under spatial statistics. And we have the first one is a median filter. Now, the reason we would use a median filter is because we can remove extremes. And so salt and pepper noise, you can see salt and pepper noise here with the black and white specks all over the image. And so if we're trying to get rid of that, that's all interference that's happening. If we're trying to get rid of that, we don't want the high and low values to impact the actual image itself, right? Because if we have a lot of black spots in one area, or for example here we have a lot of white, so this should be a black area, but if I were to take the average, it would actually gray this area out. So I want to use a median filter and find out what is the middle value of that area. So I write the whole filter out, the whole size of the filter. Again, it's just an empty window again. 3x3 filter. Write it all out and I choose the middle number. And then that becomes my middle value here. Again, you can see the major difference between 18.7, 19.6, and now 15. But now I don't have the extremes impacting my values. Okay. So that's why we would do a median filter, and it is really good for this salt and pepper noise. Then there's other statistics filters like maximum filter, minimum filter, mode filter. So maximum filter is the highest value. Usually you'll use that for really dark images if you're confident that there's not that much of, there's not a lot of noise. Minimum, it's for whitewashed images, so trying to kind of generalize what's going on if it's too whitewashed in a certain area or overall. So it does make the bright images darker. There's also mode. So mode is, in statistics, it is known as the most common number. So the most common value we would use. Now this says it's being used in homogeneous areas, so it's only really good for like crops, maybe sandy areas, like where it's all sand, like a desert. So anything that's really truly homogeneous, that's when we'll use the mode filter. Otherwise, because all we're trying to do is just like get rid of any error in that area and be like, look, it is all the same. So we can apply a mode filter and we can make those adjustments. So the next one is sharpening filters. This is where we're getting into, it's kind of a blend between the frequency filters and the spatial filters. So sharpening filters is like an edge detection technique. So there are two kinds of sharpening filters. The first one is a first derivative filter. And so this one just highlights the changes in the digital numbers. It's very sensitive to the changes though, and it creates a thick black line. So you can see here that we can see a really thick line where we're seeing changes between the two edges. And but you can still really highlight the edges of what we're seeing. The thing is that this is considered a city block. So it looks at vertical and it looks at horizontal, and it tends not to identify things that are like very curved. So that's why you can see like on this side, even though it's very clear here, it's not showing up very clear over here, and kind of the same over here. So the city block attempt is that it doesn't work diagonally as well as vertically. Even I guess it kind of works diagonally, but it's not as powerful as the second derivative. So here's an example of what we call a Sobel operator. And so it has positive values on one side and negative values on the other, and then it's zeros in the middle. So if you add that all up as if it's going to be like a weighted filter, you're going to see that the total number comes to 0. We can't use that to identify we can't use it to identify always talking to a computer starts to get so when you apply a Sobel operator, you can't apply it in the same way as you're applying the spatial filters. So spatial filter, you take the grid, you put it on top, and it's done. Sobel operators are not like that because you can't take an average of like a weighted average, because you'd be dividing by 0, and that's no good for anybody. So we do the first derivative with that. So we apply these Sobel operators, and then we take the derivative of what functions we're seeing within it. I'm not going to get into the math, but when you do apply the Sobel operator, then it's faster than the second derivative, but a little bit more bulky. So like you can see really thick lines in certain areas there. The second derivative filter, this one is a little bit more refined, but it does pick up a lot more noise. So it highlights all the changes in the digital numbers. It says it's a little less sensitive to change, but it is more sensitive to noise. So I know that makes it confusing. It does create thinner lines, and it does cause double responses. So that means double lines at times. So if you look really carefully at these images, especially this one here, you're going to see that you might have 2 lines. And then up here, we've also got like a very clear representation of this particular graph. So, or not graph, it's a Sudoku. But so we have our image, we apply Laplacian, we apply Sobel at the bottom. And the second derivative is taking a second derivative, but this time around it does both chessboard and city blocks. So we're not looking at zeros anywhere in my mask. And if I do have zeros, they're spread out. They're not like all grouped together. And we call the examples I'm giving here are called the Laplacian mask. So you can see how it's applied all around. And if you were to add it all up, it becomes 0. So that's why we have to use the derivative. So Laplacian, with one time with Laplacian, it's everything, right? So you can see that you get vertical, you get horizontal. There's also a second derivative in Sobel, but Sobel looks specifically at x and y. So you can see how x looks and you can see how y looks. So it really identifies those edges all the time. Then we have frequency filters. And with frequency filters, it is these ones are now the really complicated ones. These ones you have to apply Fourier transforms to them to be able to move them into the frequency domain, and then you're going to apply a filter in the frequency domain, then you bring it back. So of course I'm not going to get a lot of get you to do a lot of the math on that. But here we have a spelling error, good old spell check. So that's my fault. I will fix that. But here it talks about high and low spatial frequencies, not special. There's a lot of errors in this one that I totally didn't check when I went to go record. So what we're trying to do with frequency filters is we're really trying to suppress certain frequencies. So what is a frequency? If we have high spatial frequencies, the spatial frequencies, that's when we have a lot of changes all over the place that are happening. So a city, for example, has high spatial frequency because there's a house, there's a tree, there's a driveway, there's a patio, there's a deck, there's a garage, there's a garden, there's like all this stuff going on. It has very high spatial frequency. So if we want to kind of smooth it out, we would apply a frequency filter that we want to get rid of the high frequencies. Low spatial frequencies are homogeneous areas like crops. So if we're trying to emphasize the high frequencies in a homogeneous area, then we want to suppress the low frequencies. So the workflow that we have input preprocessing, apply the input preprocessing, which we do, and then we apply a Fourier transform to the preprocessed image. Then we apply a filter function to the Fourier transformed image, and then we inverse it back, so it goes back in the spatial domain. Then we process it, then we post-process it, and then we get a final image. That's how these work. But if we go into the frequency filters, there's 4 major ones. The first one is a low pass filter, so it cuts off the high frequencies. So when it says low pass, it says allow for the low frequencies to go through, and we can use those. So you can see over here we have our original image, and with a low pass filter it really smooths it out. So it's really trying to bring out the homogeneous side of that image itself. Then we have high pass filters, so this one cuts off the low frequencies. These are often used to emphasize edges. So there are 3 major, low pass, there's a couple examples of Gaussian and Butterworth. I did not come up with that, I promise. But it's just a cool filter to know, right? High pass, we have Laplacian that's added to the list as well. So we look at the high pass filter over here, you can see how the edges are identified, and it's pulling out even the grass itself, like you can really make out the grass blades in there. We also have notch filters. So notch filters are, they're like holes. So they'll say, okay, we're going to only allow these certain frequencies through. These are for really specialized applications. We don't tend to use them a whole lot in remote sensing. So, but you will find them occasionally in software. So if you ever see something saying a notch filter, then that's what it comes with. The last one is homomorphic. And this one, this one actually like incorporates changing throughout. So it goes through and it's like, oh, this is a homogeneous area. I'm going to emphasize it as a homogeneous area. So I am going to have a low pass filter. And then it moves through a city and it's like, oh, this is really high. Like there's a lot of high frequency going on. So I want to emphasize this. So it's going to change. So it really adjusts as it goes. And it's really automated nowadays. So and a very expensive software if you want to do it. But it doesn't enhance the image, and it also compresses the image. So that makes a really good change there. So that's it for that objective, but I want to show you guys a really quick example here as to how to do this math. So there's also like the edges of the image itself and how do we handle it. So there is often in Excel here, I'm going to copy that. And I'm going to put that down. So one of the ways that we can handle edges with our filters is just to leave them as they are. So then that means that the only things that we're applying the filter to is in the center there. If I'm applying a mean filter, I can take these 3 and I'm going to take the average of them. And I'm going to place the average right here. Why? Because this 9 cell window is going to be applied right here. So if I go like this and go average, and then I'm going to apply it to those ones and press enter, and there's my new value. Now I can do the same thing with the next one. So I'm going to go average, take that, and then I'm going to move it over because now I want this pixel, right? This one needs to be in the center. So I'm going to use that and then press enter. And then I can go to this one and I'm going to use the next ones. And I apply it to those and press enter. As you can see that now these are the averages of each of the 3 filters that I've applied. Now if I want to do the next one, it is exactly the same thing. So I'm going to use average, and then I'm going to highlight those, the 3x3 matrix, and I get my average for that. Notice how I am going up to the image itself, so the original, to do this, right? And go like that, and all the way down, okay? So that is how we would do the average. This is one way to deal with the edges, like I said, just leaving them as is. Another way to do them is to apply a buffer. So the buffer itself would be that I would actually expand out my edges. So if I were to take this and move this over, like that, now I can expand out my edges. And what my edges look like are going to be the same value that they're touching. Just like this. Oops, 81. See how the image gets bigger? So if I'm trying to change this value and I'm using a buffer for it, what I need to do is have my 3x3 all around that corner like that. And now I can apply my average like so. And I would apply that same filter to that corner. So now you can see it went from 112 to 146, but because of the 250 that is there than 200. So that has obviously an impact on that. So that is the buffer way of handling those edges. The last one is what we call a zero edge. So if we were to just go back to the original image, I'm going to move this back over. Go back to the original image, and all I need to do is say, okay, well, I'm trying to deal with this 112, for example. So I'm going to take these 4, and I'm going to take the average of those ones. Actually, I'll do it over here just so you can see this. So I can go equals and average, and then I'm going to collect those, and it gives me my value. Now, as I move down the edge, for example, this one's 16, I can go average. Now my whole image is the rest of it is using a 3x3. So now I can use a 3x6. I would just, or 2x6, not 6. I'm seeing the 16, 116 there. I keep saying the 6. So the 2 columns and 3 rows, there's 6 elements in there. So I'll use that and then I'll carry on. What you're trying to do is imagine that these are all zeros. Like this. So you're using a 0 buffer. So these don't matter, so you're just actually adjusting to what only has values in it. And you're trying to keep it as a 3x3 filter to go through. So weighted mean is the multiplication side of things. So we have the, we can go with like 0.25, like what I was showing before. Oh, it's good. It's only, I've adjusted this so it doesn't show any decimals. So it just change that to, okay, there we go. So 0.5. So there is my weighted mean filter. So now what I need to do is it's going to be a little bit more work. I'm going to do that. Oops, I need to have brackets first. Yes. So I'm going to do this times this plus this one times this one plus this one. As you can see what I'm doing. So I multiply each of my elements by the weight. Oops, that one. And then down here, this one takes a little longer to type out. So this one's where you have to be really careful that you are actually highlighting the right boxes based on your filter. And then that one, we finally got that whole filter filled in. And then we divide it by the number of the weight, the sum of the weight, which in this case is 4. So I add 0.25 plus 0.5 plus 0.25 all the way around. And there's my new value. So that's the value that I would be using when I go to put it into this location here, okay? So that's the weighted mean. That's how you need to be given the weight to know which one. As you get more experience, you don't need to actually measure that. The median, I would have to write them all out. So for example, I'm going to put them into numerical order in the first 3. So I have 40, and then my next one would be 81. And then the next one would be 112, and then 128, then 169, then probably 206, 216, and 241, and 250, right? So I should have 9 elements. So I've got 1, 2, 3, 4, 5, 6, 7, 8, 9. Perfect. So there's my list. Counting over, so I know that the 5 is the middle number. So I have 1, 2, 3, 4, 5. So my new value would be 169. And that would be the new value that I would use in my image for this 206 location. Okay. Maximum and minimum, that one should be pretty straightforward. Mode is a little bit trickier because this is not a homogeneous image. So I really don't have any answers that would match that, except maybe down here. If I was doing this lower level one, I think my answer would be 188 because there's 2 of them. So mode is, like I said, not as commonly used anyways, but it is an example of that. So I will have this in your, now we'll do a discussion on this and get a little practice with it. I guarantee it's going to be on the exam as well. So take some time to take a look at this, and we will, we'll continue on from here. I guess we're going to be moving on to the rest of the module.